in the chapter on fields due to moving charges, you have discussed in very detail the two very important electrodynamic or electromagnetic potentials. Actually, those potentials were the magnetic vector potential A and the scalar potential phi. In today's lecture, our aim is to find the expression for Lorentz force in terms of these electromagnetic potentials A and phi. This is a very simple problem, but very important for your examinations, different examinations, you can say. You know very well how we define the Lorentz force acting on a point charge moving in an electromagnetic field. You know that if we consider that a point charge Q is moving with a velocity v in an electromagnetic field where the electric and magnetic field vectors are E and B. It means in the electromagnetic field, the electric field vector is E and the magnetic field vector is B. And if in this electromagnetic field you consider that a point charge Q is moving with a velocity v, then you know very well that the Lorentz force acting on the point charge is simply the vector sum of the electric force and the magnetic force acting on the particle. And you know, the electric force acting on a charged particle Q in an electric field E is given by Q times E, and the magnetic force is given by Q times V cross B. So the vector sum of these two forces will be simply what? That will be F equal to Q times E plus V cross B. And you know this force F, which is actually the total electromagnetic force acting on a charged particle Q moving in an electromagnetic field with velocity v, is known as Lorentz force. This is the well-known expression for Lorentz force, and I hope all of you are knowing about this expression. But as I have told you that the aim of today's lecture is simply to express this Lorentz force F in terms of the electromagnetic potentials A and phi. Okay? So you have learnt in the previous lecture how these field vectors E and B can be defined in terms of the electromagnetic potentials A and phi. You know, the electric field vector E is given by minus grad phi, that is gradient of phi, and you know that grad phi is written as del phi. So E is equal to minus del phi minus del A by del T. You have studied these things, okay? And at the same time, you know that the magnetic field vector B is defined as curl of vector A, where A is the magnetic vector potential. And this curl of A, you know, this can be written as del cross A. So these two expressions actually expresses the electric field vector E and the magnetic field vector B in terms of the electrodynamic potentials phi and A. And you can see that in the expression for the Lorentz force defined in this equation 1, you can see that there is an electric field vector E in the term in right side, and the term B also in the right side. So to express this Lorentz force in terms of phi and A, we will simply use this equation 2 in equation number 1. It means at the place of E, we will simply write minus del phi minus del A by del T. And at the place of vector B, you can write curl of A, that is del cross A. So let us make the use of this equation 2 in this equation 1. So after using equation 2 in equation 1, what will be our result? You can see easily. you can see I have mentioned it here that F will be equal to Q times E plus V cross B. So instead of E, I have written here, you can see minus del phi minus del A by del T and plus V cross B. And you know B is equal to del cross A. So B has been replaced by del cross A. Okay. Now we will simplify the RHS of this equation by using the formula of triple vector product. In fact, this last term V cross del cross A will be simplified by using the formula which you study in vector algebra for the triple vector product. So what will be F? This will be Q times minus del phi minus del A by del T and plus. Now V cross del cross A, from the formula of triple vector product, you can write this expression as del V dot A, del V dot A and minus V dot del A. You know, this is actually based on the formula for the triple vector product. Now let us arrange the terms in RHS to some extent. You can see we can write this as, this is Q times minus del phi minus del A by del T. I have actually taken this minus as a common factor, so del A by del T will be written positive and plus V dot del A. You can write, since minus has been taken as a common factor, so this term is negative, so I have written here positive. Okay, and plus the remaining term is what? The remaining term is this much. This is del operated on V dot A. Okay, this is a very simple calculation, you can easily understand. Okay, and let us say this is actually the expression for the Lorentz force F, and we simply write it, this is equation number 3. Okay, now our aim is actually to evaluate this term inside this curly bracket. Our aim is to evaluate this, and for this you know that the magnetic vector potential A is actually a function of the space coordinate r and the time t. And you know this r is simply actually equal to xi plus yj plus zk. So in a scalar form, you can say that this A is actually a function of what? This will be a function of x, y, z and t. It means this magnetic vector potential A is actually a function of 4 independent variables. And those 4 independent variables are what? Those are x, y, z and t. Now let us try to find the ordinary derivative of this magnetic vector potential A with respect to t. It means we are going to evaluate dA by dt. As you can see that this vector potential A is a function of 4 independent variables, and our aim is to find the time derivative of this A. So you must follow the rules of partial differentiation, and you know this rule very well. So what will be dA by dt? You can see this will be simply del A by del x times dx by dt. Okay, plus del A by del y times, can you say, that will be simply dy by dt, okay, plus del A by del Z. Can you say what will be the multiplicative factor? That will be dz by dt, and plus del A by del t times dt dt, okay. This expression has been written on the basis of rules of partial differentiation, and that is well known to you, I hope. Now you know this dt dt is equal to 1, okay, and what is this dx by dt? You know this dx by dt is vx. This is actually the x component of velocity. Similarly, this dy by dt will be written as vy, which is y component of velocity vector v, and dz by dt will be written as vz, which will be actually the z component of velocity vector v. So you can write this expression as, this is vx. Instead of this dx by dt, I have written here vx. So this is vx del A by del x. Similarly, dy by dt, what is this? You can say this is vy and times del A by del y, and plus dz by dt is vz, and this is del A by del z, okay, and plus since dt dt is 1, so the last term will be what? This is del A by del t, del A by del t. Now can you say this expression, the sum of the first three terms will be what? We can write this. You can easily write this expression as dA dt. dA dt. This may be written as v dot del A plus del A by del t, del A by del t. In fact, you can check it that this v dot del A is equal to what? You know, v is vxi plus vyj plus vzk. So this can be written as vxi plus vyj plus vzk, okay, and dot del, and you know I am writing it here. You can see I am writing it here. Instead of del, you can write del xi plus del yj plus del zk, and this is operated on the function a. Now when you will take this scalar product of vxi plus vyj plus vzk with this much, you know, in a scalar product only the similar terms are non-zero and all other terms will be zero. So this will be simply vx times del x plus vy del y plus vz del z, and this is operated on vector A. So finally you will get what? This is vx del A by del x plus vy del A by del y and plus vz del A by del z. So what you are seeing here, that so we can see that v dot del A is simply equal to this much. So instead of this expression Vx del A by del X plus Vy del A by del Y plus Vz del A by del Z, I have written here this term V dot del A. I hope you have understand. And this I have simplified it only to understand. In examination there is no need to write this calculation. You can write directly that this V dot del A is simply equal to this much. Okay. Now this result which we have obtained in this equation 4, we can use this result in the equation which defines actually the Lorentz force F, which is defined actually in equation 3. So you can see actually we have evaluated that the expression inside this curly bracket, that is del A by del T plus V dot del A, instead of this you can write simply this dA by dt. dA by dt. You can write it. So now we will write dA by dt instead of that expression in equation 3. So using equation 4 in 3, we get what you will get. You can see easily. The expression for F now will be what? You can see the expression that is equal to Q times minus del phi minus dA by dt. This dA by dt has been written instead of this, you can see. Okay. And plus the remaining term. And what is the remaining term in that expression? You can see that is simply del V dot A. Del V dot A. You can see the expression here. This is del V dot A. Okay. So now the expression for the Lorentz force in terms of this electrodynamic potentials phi and A, we have obtained. Now we will simply write the right hand side of this expression in a suitable form. So you may write this equation as F equal to Q times minus del phi plus V dot A. Okay. You can see this operator del is operated here on phi, and in the last term it is operated on V dot A. So I have operated this minus del phi on this expression. Sorry, here there will be actually minus because this term is plus, and you have taken the minus sign as a common factor. So actually no, erase this plus sign here. There will be actually minus sign. This is actually minus, because I have taken minus as a common factor. And the remaining term is what? This is minus dA by dt. So this is actually our final expression for the Lorentz force in terms of the electrodynamic potentials phi and A. And as I have told you in the beginning of this lecture, that in this lecture our prime aim was only to express this Lorentz force in terms of the electrodynamic potentials phi and A. So this is a very important relation, and I hope you should remember it for solving the objective questions. It is possible that the expression for Lorentz force will be given in different choices, and you have to select what is the correct option for the expression for Lorentz force in terms of electrodynamic potentials. Now in the next lecture, in continuation of this, we will see that how we can express the electrodynamic potentials in terms of the electric field vector and the magnetic field vector when these field vectors are uniform. It means when the electric and magnetic field vector will be uniform, then how the electric and magnetic field vector will be expressed. You will see that in that condition the scalar potential phi will be equal to minus E dot R, and the vector potential will be equal to 1 over 2 B cross R. This will be the result, but those results we will discuss in the forthcoming lecture. So I hope you have understand how we can express the Lorentz force in terms of the electrodynamic potential.